Look around you for a second, wherever you are. Like, if you are sitting in an office, just look at the sleek, perfectly flush window frame that's probably catching the afternoon light right now.
Yeah. Or if you're on a factory floor, glance over the complex machine panels that are just humming away, keeping all those internal components protected.
Right. Or maybe you're driving past a field of solar panels. You see those structural mounting brackets holding hundreds of pounds of glass, perfectly angled toward the sun, completely enduring high winds and, extreme weather.
Oh, absolutely. And the crazy thing is, every single one of those finished, highly engineered pieces of metal began its life as something completely unremarkable.
Just a plain, heavy, unassuming block of raw metal.
An ingot.
Exactly, just a big block of aluminum.
And that is exactly what we are jumping into today. We are doing a deep dive into a really detailed guide from Eleanor Industries to help you, especially if you are a manufacturing buyer stepping into a high-stakes procurement meeting, navigate a foundational supply chain decision, right? The choice between primary and secondary aluminum ingots for specific projects. It sounds niche, but it is huge.
Okay, let's unpack this. Choosing your starting aluminium ingot is, it's essentially like a baker choosing between different grades of flour, but, with massive industrial and chemical implications.
I love that analogy, because if you want a delicate, hyper-consistent pastry, you need a highly refined, perfectly milled cake flour, right?
Exactly. If you pick the wrong raw material at the very beginning, it doesn't really matter how good your oven is. The fundamental chemistry of the final product just fails.
Yeah, and in manufacturing, your choice of ingot absolutely dictates the final product's cost, its ultimate tensile strength, and exactly how well it will hold up under immense physical pressure in the field.
And the stakes for that procurement buyer are incredibly high. It goes way beyond just a simple line item cost on a spreadsheet, right?
Oh, totally. This is a foundational material science decision that echoes throughout the entire life cycle of a product. It dictates your budget predictability for the next fiscal year in a highly volatile commodities market.
Which is terrifying for a buyer.
Right.
Yeah.
And it shapes a company's total carbon footprint and Scope 3 emissions, which is so critical for global regulatory compliance now.
Not to mention the actual physical part itself.
Exactly. Fundamentally, it determines the microstructural integrity of the metal. It's the literal difference between a high-load structural profile surviving decades of extreme stress.
Or failing catastrophically when it matters most.
Exactly.
So before we can evaluate which type of aluminum a buyer should source, we really need to establish the mechanical reality of what these materials are and, how they are processed.
Right. Let's get into the mechanics.
We are looking at two broad categories based on the source of the metal. Primary aluminium is the metal produced from freshly mined bauxite ore. So it is pulled from the earth, heavily processed, and smelted into brand new metal.
Yep. Brand new from the ground.
Secondary aluminium, on the other hand, is produced from recycled scrap metal. So old window frames, discarded engine blocks, everyday packaging, it's all melted down and given a second life.
But the ingot itself isn't the final product. It's really just the raw fuel for the extrusion plant.
Right. And to understand why that origin story dictates the final performance, we kind of have to understand the violence of the extrusion process itself.
Violence is a good word for it. When a manufacturer buys an ingot, they first cast those rectangular blocks into long cylindrical logs called billets.
Okay.
And these billets are loaded into an extrusion press and reheated to an incredibly high temperature, usually around 450 to 500 degrees Celsius.
So just below the melting point.
Exactly. It puts the metal into a state of high plasticity. It's solid, but highly malleable.
Like really hot clay.
Right. And then the press uses a hydraulic ram to force that softened metal through a shaped steel die.
And we are talking about 2,000, sometimes up to 5,000 tons of sheer hydraulic force, right? Pushing this metal through intricate, tightly designed channels to form long, continuous profiles.
It is an environment of immense shear stress. The metal literally has to split apart as it flows around the internal structures of the die.
Oh.
And then it seamlessly welds itself back together under pressure before it exits the machine.
So here is the critical question for a buyer. If I take a piece of freshly mined primary aluminum and a piece of recycled secondary aluminum and subject both to thousands of tons of hydraulic force and blistering heat to push them through that die,
Yeah.
does the metal physically remember where it came from? Like, if they both look like a shiny piece of shaped metal on the other side, does a recycled ingot behave differently on a microscopic level than a freshly mined one?
What's fascinating here is that mechanically and metallurgically, the metal absolutely remembers.
Really, how so?
Well, the purity of the original ingot directly dictates the grain structure of the metal as it flows. During extrusion, the metal needs to flow laminarly, smoothly, and evenly through the die's friction-heavy channels.
Okay, so a smooth flow is critical.
Very critical. If there are microscopic inconsistencies or trace elements in the metal, it alters the flow stress. It affects how the metal undergoes plastic deformation.
So it fights back against the machine.
Exactly. If the metal doesn't flow perfectly, you get variations in the wall thickness of the final profile. And beyond the manufacturing floor, the chemical makeup of that original ingot determines the finished profile's ultimate yield strength and its resistance to environmental corrosion over time.
So the metal's past life literally dictates its future physical performance.
100%.
Since origin impacts behavior under pressure like that, let's analyze the absolute purest option first to understand why buyers are willing to pay top dollar for it. Let's look at primary aluminum.
Okay, the premium choice.
We know it comes from raw bauxite ore, but what mechanically makes primary metal the premium choice?
It all comes down to absolute chemical control, which results in near-perfect purity. Primary aluminum boasts exceptional purity levels with virtually zero unwanted trace impurities.
Because it's starting from scratch.
Right. The reason is the smelting process. Because it is being refined directly from alumina, which is extracted from the bauxite ore, the chemical composition can be strictly controlled at the atomic level.
Oh, wow, so you know exactly what's in it.
Exactly. This gives the manufacturer highly predictable batch-to-batch consistency in the metal's mechanical properties. When you put a primary billet into an extrusion press, the thermodynamics and flow characteristics are identical every single time.
And that consistency translates directly to precision. According to the Eleanor Industries guide, primary aluminum is the preferred choice for critical load-bearing parts, aerospace engineering, defense applications, and heavy structural profiles.
Yes, because it makes it significantly easier to hold incredibly tight dimensional tolerances.
And by tight tolerances, we aren't talking about a rough approximation. We are talking about keeping the wall thickness of an interlocking metal joint accurate to within fractions of a millimeter.
Right, ensuring that complex parts snap together perfectly without any structural weak points. Precision is the exact right word.
So the lack of impurities is the secret.
Because there are no trace impurities disrupting the metal's flow through the extrusion die, the manufacturer can push the absolute limits of design geometry.
You can create incredibly thin walls that still maintain massive structural rigidity.
Which is exactly why the aerospace and automotive industries demand it. They need high strength and low weight, with literally zero margin for error.
Here's where it gets really interesting. I look at primary aluminum kind of like a Formula One race car.
Oh, I like that.
Right, it is perfectly engineered for an extreme, no room for error environment. If you are building a critical component for a commercial jet, you absolutely need that F1 level of precision.
You do.
But just like running a Formula One team, relying entirely on primary aluminum comes with brutal economic and environmental realities. As a procurement buyer, you are dealing with a massive financial burden.
The downsides of primary aluminum are stark. First, let's just look at the economics. The cost of primary aluminum is not only significantly higher, but it is deeply volatile.
Because it's tied to the global markets.
Yes, it is tied directly to the London Metal Exchange, acting essentially as a proxy for global energy prices.
Wait, energy prices. Why energy?
Because smelting bauxite into aluminum requires an intensively massive amount of electricity. It uses a method called electrolytic reduction, specifically the Hall-Héroult process.
Okay.
Massive electrical currents are required to literally tear the strong chemical bonds between oxygen and aluminum molecules apart.
So when a buyer is paying a premium for primary aluminum, they are fundamentally paying for the immense electrical brute force required to rip those molecules apart at the smelter.
Exactly, you're buying electricity, essentially.
Wow. So if global natural gas or coal prices spike, the cost of the electricity required to run those smelters spikes, and the price of primary aluminum skyrockets right along with it.
Yep, it's completely chained to the energy grid. So a buyer trying to lock in a 12-month budget is taking on a massive commodity risk.
And I imagine that immense electrical requirement directly feeds into the second major downside, the environmental footprint.
A staggering environmental footprint. Smelting primary aluminum generates massive carbon emissions.
Right.
If a company has strict environmental, social, and governance targets, or aggressive Scope 3 emission reduction goals, relying entirely on primary aluminum will completely sabotage those efforts.
And from a supply chain perspective, it's fragile, right?
Very. Because these smelters are so specialized and heavily dependent on regional power grids, capacity frequently gets tight. When smelting capacity drops, supply chain bottlenecks occur, leading to extended lead times for raw materials.
So as a buyer, you get the absolute best purity, but you pay a premium price, absorb massive market volatility, expand your carbon footprint, and potentially face supply chain delays.
It's a tough trade-off.
Because primary aluminum carries this heavy financial and environmental baggage, the manufacturing industry really had to scale up a crucial alternative. Which brings us to secondary, recycled aluminum.
Secondary aluminum is designed to completely bypass those thermodynamic hurdles of primary production. The central advantage is the staggering drop in energy consumption.
How big of a drop are we talking?
Producing secondary aluminum from recycled scrap requires up to 95% less energy than smelting primary aluminum from raw ore.
95%. That is a massive operational shift. And that comes down to the underlying chemistry, right?
It does.
Because with primary, you were using electricity to forcefully break chemical bonds. But with secondary scrap, the aluminum has already been refined.
Exactly. You don't have to break any chemical bonds. You just have to apply enough thermal heat to change the metal state from a solid back into a liquid.
Right, just melting it.
Overcoming that latent heat of fusion takes just a tiny fraction of the energy compared to electrolytic reduction.
That is the mechanical reality right there.
Right.
And because the energy requirement plummets, the carbon footprint plummets with...
Which provides exceptional sustainability credentials for corporate reporting. But that drop in energy also fundamentally transforms the economics for the buyer.
It makes it cheaper.
Much cheaper. Secondary aluminum offers lower and critically much more stable costs. It largely escapes the volatile energy and commodity market swings because it relies on locally or regionally available scrap rather than globally mined bauxite and massive power grids.
So you actually get budget predictability.
Yes.
Honestly, it sounds like the ultimate procurement hack. You hit your sustainability goals and you stabilize your budget.
It's a huge win on paper.
This is why secondary aluminum is widely utilized for general manufacturing, automotive parts, architectural construction hardware, modular furniture, and packaging.
Yep, it's everywhere.
But let me step into the shoes of a skeptical buyer looking at a spreadsheet right now. If secondary aluminum is drastically cheaper, price stable, and slashes my carbon reporting, why wouldn't I just mandate it for every single component I buy? What is the actual metallurgical catch?
Well, the catch lies in the trace impurities, specifically intermetallic phases.
Okay, unpack that for me.
It depends entirely on where the scrap metal was sourced and how rigorously it was sorted before melting. Secondary ingots frequently carry trace elements like iron or silicon.
Because it's mixed scrap.
Right. When you melt down a massive batch of scrap, say a pile of old window frames, you're also melting down whatever alloys, coatings, or stray screws were mixed in with that material. This introduces major chemical variability.
Ah, I see. So if I melt down a window frame that had a few steel screws left in it, that iron gets into the molten soup.
Exactly.
And earlier we established that the metal remembers. How does that trace iron physically manifest when you try to extrude it?
Iron is particularly problematic because it doesn't dissolve perfectly into the aluminum crystal lattice. Instead, it forms alpha-C intermetallic phases.
Which means what exactly?
Think of these as microscopic, hard, brittle particles suspended inside the softer aluminum matrix.
Oh, wow.
So when you take that secondary billet and force it through the extrusion die at 2,000 tons of pressure, those hard iron particles do not flow. They drag against the intricate steel channels of the die.
So it is kind of like trying to force a handful of tiny pebbles through a high-pressure water hose.
That's a great way to picture it.
The pebbles disrupt the smooth laminar flow of the water. In the metal, those hard iron shards cause friction, leading to micro-tears on the surface of the profile, totally ruining the architectural finish.
Or worse, they create internal stress concentrators inside the metal.
Internal stress points, that sounds bad.
It is. That is the exact mechanism of failure. Those micro-tears and internal stress points severely compromise the structural integrity.
So it becomes brittle.
Right. Because of this unpredictable variability, secondary aluminium is generally ruled out for ultra-high specification, aerospace-grade work, or extremely critical heavy load-bearing structures where there is absolutely zero tolerance for variation.
Because the final yield strength of a secondary ingot is entirely at the mercy of the recycling and sorting process.
Exactly.
Wow. This leaves the buyer facing what looks like a brutal binary choice. Option A, expensive perfection. Primary aluminum gives you pure, predictable, aerospace-grade precision, but blows up your budget and your carbon footprint.
Yep.
Or option B, eco-friendly variability. Secondary aluminum saves your budget and hits your sustainability targets, but introduces brittle impurities that could compromise critical structural parts.
It's a tough spot for a buyer.
Do buyers actually have to choose one extreme or the other?
In a fragmented supply chain, they often do. But this is where sophisticated manufacturing operations break the binary. Many of the most advanced extruders don't force a strict choice. Instead, they carefully blend primary and secondary ingots together to create a custom alloy mix.
So it's not just one or the other. Let's bring in the specific operations of Eleanor Industries here, because their guide details exactly how this works in practice. They are recognized among the top aluminium extrusion companies in India, operating a massive modern plant in Gujarat.
Yes.
And what makes their approach to blending so effective is their operational model. They manage everything end to end under one roof. They handle the ingot sourcing, the melting, the billet casting, the actual extrusion process, and the final finishing.
And that end-to-end control is the absolute prerequisite for successful blending.
Why is that?
Because if you are going to mix pure primary metal with variable secondary scrap, you cannot afford a disconnected supply chain where one company casts the billet and a completely different company extrudes it. You need real-time chemical control.
So what does this all mean for the chemistry? Blending primary and secondary aluminum is essentially a high-stakes dilution process.
Yes, exactly.
Like a master chef mixing a high-end, expensive ingredient with a reliable, everyday staple to create a perfect, cost-effective dish. If a manufacturer has a batch of secondary scrap that they know has slightly elevated levels of trace iron, they can melt it down and carefully introduce highly pure primary aluminum into the furnace.
Right. The pure primary acts to dilute the iron concentration down to an acceptable parts per million threshold, mitigating those brittle intermetallic phases we talked about.
So you end up with a blended billet that has near primary mechanical performance, but at a drastically reduced cost and carbon footprint.
If we connect this to the bigger picture, that dilution process requires intense technological oversight. A facility like Eleanor's in Gujarat utilizes optical emission spectroscopy, or OES.
What does that do?
Before they cast the blended molten metal into a solid billet, they spark a sample of it and analyze the light spectrum to determine the exact chemical composition down to the elemental level.
Wow, so they know exactly what's in the pot.
Exactly. They know the exact percentage of iron, silicon, and copper in the melt in real time.
Because they control the melt and the extrusion press, they know exactly how that specific chemical recipe is going to flow through the die.
They take the guesswork entirely out of the procurement process. You aren't just buying a block of metal, you are buying the manufacturer's metallurgical expertise and their ability to manage that metal's chemistry from the furnace to the finishing line.
This level of closed-loop control allows the manufacturer to guarantee the absolute consistency of that blended recipe.
Right, they can adjust the ratio on the fly to ensure the metal flows perfectly without micro-tearing.
Which ensures the buyer hits both their strict corporate sustainability targets and their budget constraints without ever sacrificing the structural yield strength of the final product.
Exactly. It's the best of both worlds.
Let's synthesize this into a definitive toolkit for you, the buyer, based on the Eleanor Industries guide. If you are building aerospace components, defense equipment, or hypercritical high-load structural parts where a microfissure could lead to catastrophic failure, you need the absolute purity, tight dimensional tolerances, and batch-to-batch predictability of primary aluminium.
No question about it. You have to pay the premium and absorb the carbon footprint for that F1 level of precision.
Conversely, if you are procuring general-purpose architectural profiles, standard hardware, modular furniture, or everyday automotive trim, and your primary directives are to hit a strict budget while achieving aggressive Scope 3 sustainability goals, secondary recycled aluminium is your undisputed go-to material.
Totally.
And for the vast majority of highly engineered projects that sit somewhere in between those two extremes, where you need near primary structural strength but desperately want the environmental and cost benefits of recycling, you need to leverage custom blending.
But you must partner with a manufacturer who utilizes real-time spectroscopy and controls the entire process end to end. So the chemistry is tightly managed.
Right. It takes real expertise.
It does. And this actually raises an important question about the future trajectory of the global supply chain.
Okay, what are you thinking?
Well, we have established this deep tension between the flawless purity of primary metal and the trace impurity risks of secondary scrap. But the technology surrounding scrap segregation is rapidly evolving.
Oh, really? Like how?
The industry is beginning to deploy advanced AI and automated spectroscopic sorting on conveyor belts, analyzing and separating scrap at lightning speed before it ever hits the furnace.
Oh, wow. So if the automated sorting gets good enough, it prevents the iron from ever getting into the soup in the first place.
Precisely. So the final thought to consider is this. As sorting technology inevitably becomes more advanced, and we perfect the ability to strip out those trace impurities from the scrap pile at a massive scale, will the mechanical performance gap between secondary and primary aluminum eventually vanish entirely?
That is wild to think about.
Right. Could we see a future where a zero-tolerance aerospace-grade component for a commercial jet is reliably forged entirely from recycled soda cans and old window frames?
A completely closed-loop system where the thermodynamic burden of smelting bauxite is left in the past, and the metal truly gets an infinite, structurally perfect second life. That is an incredible thought to leave on. Thank you for joining us on this deep dive into the Eleanor Industries Guide.
It's been great.
The next time you walk past a sleek window frame or inspect a heavy structural bracket, we hope you view it not just as a piece of metal, but as a marvel of thermodynamics, supply chain economics, and immense hydraulic force. Keep questioning the physical world around you.